Let's see how we can use a sine graph to model a basic periodic function. In this case, we're looking at the average temperature in the United States between January 2018 and July 2021. This data is from the website Statista. And if I put my mouse over each of these dots, I can see what the temperature was in June, for example, in this case 2018, 2019, and 2020. And what I've done is I've taken this data and imported it into GeoGebra for two of the years, 2018 and 2019. So here's our data. And notice I've taken the months and assigned values to them, starting with month 0, which is the January of 2018, and all the way to 23. So that's 2 years worth of data, and these were the temperatures at each of those months from that table. Here you can see that graph plotted, and on the bottom you can see a basic sine graph, just one sine x, right? So no shift vertically or horizontally, and the period is still 2 pi, and the amplitude is 1. So what we want to do is then take this graph and try to make it fit the dots that we have. Right, so the first thing we're going to try to do is see how much vertical shift we have, right? So that clearly this graph has a vertical shift because a typical sine graph would have gone below the x-axis, and here the x-axis is along this typical sine graph. So the easiest way to do that is to take the average of the highest point and the lowest point in my graph. So in here I have actually picked these points, at least visually they appear to be the highest or lowest. So I'm going to take the average of 75.45 and 32.56 by just adding them and dividing them by 2. Right? So if I take 75.45, add it to 32.56, and divide my answer by 2, 75.45 plus 32.56, is 108.01, and then dividing that by 2, I get 54.0005. I'm just going to round that to 2 decimal places, 54.001. So what that means is if I shift a sine graph up by 54.01, so let me do that, 54, okay, so 54 in this case is best I can do, I believe. Yes. Okay, so 54 roughly. And that, notice, it's roughly where the middle of this graph is going to be. So next thing we want to do is figure out what the amplitude's going to be in here relative to this new line. And again, that line, the shift, is halfway between the highest point of my graph and the lowest point of graph. So all I have to do is find the difference between my maximum value here and the value of the line that I found, and that should tell me how much the amplitude is. I can do this for either of these. The answer is going to be a little off because we're just modeling, right? So this is not going to fit perfectly, but we're going to find the closest graph or closest equation we can get to fit our dots, right? So if I take 75.45 and subtract 54.01 from it, right? So 75.45 minus 54.01 is 21.44. Right, so that's really the difference between didn't mean to move it, is the difference between that point and our line. All right, so 21.44. So if I go and move this up to 21.44, and I'm going to do my best I can to get close to it. We notice that that graph is now almost where our original graph is, but it has still a few issues with it. Number one, the period doesn't match. There are way too many cycles of this graph in the 2-year period that we are looking for, right? So next thing I need to do is adjust the period of this graph, and that, if you recall, is done by changing the coefficient of this equation. Right, so that's number b, right? So typically, if I write this equation as y equals a sine of b times x minus c plus d, right? So this is all inside of a sine. The b is what dictates what the period of this graph is. And as a formula, we have 2 pi divided by the period is going to give me b, right? Or 360 degrees. In this case, we're not measuring our dates in degrees, so I'm just going to stick to the radian. So I have to take 2 pi and divide it by the period. And in this case, I know what the period is going to be. It's a year, which would be 12 months. And our units are in months, right? So I got to take 2 pi and divide it by 12. So, so 2 pi is roughly 6.28. We're just carrying 2 decimal places here. So I'm just going to stick to that and divide that by 12. I get roughly 0.52. Okay, so let me just adjust my b to be 0.52. There we go. So now that graph looks like it has the right cycle. The only thing I now need to do is adjust its phase shift. It is a little farther to the left of where my data was, and I need to adjust it to make sure it comes to the right a little bit. That means I have to find out the value of c. Right, so the value of c is in our equations what dictates how far left and right our graph is, the phase shift of our graph. And to do that, what I'm going to do is take one of the points on my graph. It doesn't matter which one. So I'm just going to take maybe this one right here, 4 and 65.52. So 4 and 65.52, and plug them into our equation, which at this point we know the a for. The value of a was 21.44. Sine of a, which we had found to be 0.52 times x minus c plus d, and d was the first value we had found, right? So this was d, and this was a. So plus 54.01. And we plug our x and y into this equation. So I would have 65.52 equals 21.44 sine of 0.52 times 4 minus c plus 54.01. And solve that equation for c. So to solve that equation for c, first thing I'm going to do is subtract the 54.01. So I'm going to have a 65.52 minus 54.01 equals 21.44 sine of 0.52 times 4 minus c. Divide by 21.44, so 65.52 minus 54.01 is 11.51. Divide that by 21.44. I have sine of 0.52 times 4 minus c. Take the inverse sine. So let me move this up a little bit. Take the inverse sine. So I'll have sine inverse of 11.51 divided by 21.44 is equal to 0.52 times 4 minus c. Divide my answer by 0.52, so I have sine inverse of 11.51 divided by 21.44. Divide that by 0.52, and that's equal to 4 minus c. So I'm going to punch that all in the calculator at this point. Divided by 21.44, inverse sine of that is 0.566 or 0.57 divided by 0.52. So 0.57 divided by 0.52 gives me 1.096 or 1.1. So next thing I'll do is subtract the 1.1 and move the c to the other side. So c would be 4 minus 1.1, and that is 2.9. Roughly, right? So all of these are approximated. So if I go back to my function and now adjust c to be 2.9, I should have a pretty decent fit for my function. So notice it's not perfect, it's modeling, and the temperatures are not exactly the same throughout. But it gives me an equation where I can use to predict temperature in the future and maybe see if there is any changes in the temperature as opposed to what we expected.